Welcome back to my channel. Today we are talking about RC circuits. And joining me today for the presentation is Giselle the Gazelle. Thank you very much. Giselle decided to join us today for the presentation because she has an intense interest in RC circuits. Giselle, why do you have such an intense interest in RC circuits? Because she likes things that change with time. And in an RC circuit, the circuit parameters change with time. Here is an RC circuit. We have a battery with a battery voltage VB. It is connected to a switch S. We have a resistor R and a capacitor C. When the switch is closed, the current through the circuit, the voltage across the resistor, and the voltage across the capacitor, and the capacitor charge will vary with time. And we can measure the voltage across the resistor and capacitor by connecting a voltmeter, or voltage probe, across the circuit element. What we will consider today is the circuit parameters, the values of those parameters, immediately after the switch is closed. Those are called the initial parameters. And then we will look at the circuit parameters a long time after the switch is closed. And those are called the steady state parameters. Let's look at the circuit which we built. I am now joined by Giselle the Gazelle. This is the circuit which we built. We have a battery. The positive terminal of the battery is connected to a switch, which is connected to a resistor, 5.6 kiloohms, and the resistor is connected to a capacitor, 220 microfarads. The capacitor is connected to the negative terminal of the battery. They are all connected in series. When I close the switch, the capacitor will begin charging. During this process, I want to measure the voltage across the resistor and the voltage across the capacitor as a function of time. To do that, I will be using two differential voltage probes that are connected to a LabQuest, and the LabQuest is connected to the computer. Before I begin, I want to ensure that the capacitor is completely discharged. So I'll use a wire and I'll connect the two terminals of the capacitor together. That will discharge the capacitor. The capacitor is now discharged. I will also zero the two voltage probes at this time. The voltage probes are now zeroed. Okay, we can now begin the experiment. Giselle, could you please press the button on the mouse to start data collection, and then I'll close the switch, okay? Great. Thank you. Now I will close the switch. The capacitor is now charging. I am collecting 1,000 samples per second for 15 seconds. The data is coming along. Our next step is to analyze it. This is the data which we obtained. At the top is a graph of resistor voltage versus time, and at the bottom is a graph of capacitor voltage versus time. You can see that the resistor voltage starts high and then goes to zero and remains constant, whereas the capacitor voltage starts at zero, increases to a constant value. If we use Ohm's law, we can find the current through the circuit. We apply Ohm's law to the resistor. The current is VR over R. So I divide the voltage across the resistor by 5.6 kiloohms. And this is what we get. The current through the circuit. The current starts at a high value and then falls to zero and remains constant. If we use this relationship, the charge on the capacitor is given by the capacitance times the voltage across the capacitor. Using the capacitance of 220 microfarads, we get this. The charge Q starts at 0 and then increases to a constant value after a long time. Here are the initial and steady state parameters which we obtained from the data. The voltage across the resistor, VR, starts at 1.49 volts and then reaches a steady state value of 0.006 volts, essentially 0. Whereas the capacitor voltage starts at 0.009 volts and increases to 1.49 volts. 1.49 volts is the voltage across the battery. So initially, all the battery voltage is across the resistor, and then, in steady state, after a long time, all the battery voltage is across the capacitor. Let's look at the current. It starts at 0.266 milliamps and then falls to 0.001 milliamps, essentially 0. And the charge in the capacitor starts at 1.9 microcoulombs and increases to 328.1 microcoulombs. Here's a summary of what we find for the initial values of the parameters. Initially, the current is maximum. The charge on the capacitor is 0. The voltage across the capacitor is 0. All battery voltage is across the resistor, and the capacitor offers no resistance to current. The capacitor acts like a short circuit. So we can replace the capacitor in the circuit with a straight wire, just like this. And so now when we analyze this circuit, in the initial conditions, immediately after the switch is closed, we get this. Just by applying Ohm's law, I equals the battery voltage divided by the resistance. Now look at what our findings are for the steady state condition. The current is 0. The voltage across the resistor is 0. All battery voltage is across the capacitor. The charge on capacitor is maximum, and we get that charge from this relationship. Q equals C times the battery voltage. And the capacitor offers complete resistance to current. The capacitor acts like an open circuit. So in our circuit, we can replace the capacitor with an open circuit. It's as if we just cut the wire at this point. And then, of course, no current is going to flow through that circuit. Let's look at some examples to illustrate these concepts. The capacitor in this circuit is initially uncharged. We want to find the circuit parameters A, immediately after the switch is closed, and B, a long time after the switch is closed. Let's first look at immediately after the switch is closed. We close the switch. A current I starts to flow through the battery. At this junction, it splits up into two parts. There's a current I1 through the 8 ohm resistor and a current I2 through the capacitor. Now we know, as we just saw, immediately after the switch is closed, we can replace the capacitor with a short circuit, like this. And this short circuit has 0 resistance, as shown here. Now let's look at these 2 points, A and B. Since they are connected by a 0 resistance wire, there must be no potential difference between the 2 points. So VA minus VB equals 0. If that is the case, then the current I1 must be 0. Because if the current I1 was not 0, then there would be a voltage drop across the 8 ohm resistor, and VA would not equal VB. So I1 equals 0. And at this junction, at junction A, if we apply Kirchhoff's junction rule, we know that the current into the junction, I, equals the currents going out of the junction, I1 plus I2. So since I1 is 0, we find that I2 equals I, the current through the battery. So really we can just get rid of that 8 ohm resistor. And our circuit becomes this: a 12-volt battery with a 4 ohm resistor. Let's apply Ohm's law. I equals V over R. 12 volt for the battery divided by the 4 ohm resistor, we get a current of 3 amps through the battery. Now let's look at more circuit parameters. I is 3 amps, I1 is 0 amps, I2 is also 3 amps. Let's find the voltage across the 8 ohm resistor. As we saw before, it is 0 volts because I1 is 0. The voltage across the capacitor is the same as the voltage across the 8 ohm resistor because they are connected together. And so the voltage across the capacitor is also 0 volts. And the voltage across the 4 ohm resistor must be 12 volts. The entire battery voltage is dropped across the 4 ohm resistor. And you could also find this by applying Ohm's law. V equals IR. So we have a 3 amp current through a 4 ohm resistor. 3 times 4 equals 12 volts. The charge on the capacitor. QC equals C times VC. And since VC equals 0, the charge on the capacitor is 0 coulombs. Now let's look at V. A long time after the switch is closed. So we close the switch. Current I flows through the battery. At this junction, it breaks up into 2 parts. Current I1 through the 8 ohm resistor and current I2 through the 6 microfarad capacitor. After a long time, as we saw earlier, the current through the capacitor is 0. So I2 equals 0. Applying Kirchhoff's junction rule at this junction, current in I equals the current coming out, I1 plus I2. Since I2 is 0, we find that I1 equals I. Now, we can just get rid of that capacitor. It's really can be considered an open circuit. So our circuit becomes this: 12-volt battery with 2 resistors in series. The equivalent resistance is 4 plus 8 equals 12 ohms. So our circuit becomes this: 12-volt battery across a 12 ohm resistor. Let's apply Ohm's law to find the current I. I equals V over R, which is 12 volts over 12 ohms. It's 1 amp. So the current through the battery is 1 amp. Let's find the other circuit parameters. I2 equals 0, as we saw before. I1 equals I, so it equals 1 amp. Now the voltage across the 4 ohm resistor. Let's apply Ohm's law. Current of 1 amp times resistance of 4 ohms, we get 4 volts. The voltage across the 8 ohm resistor. Current of 1 amp times resistance of 8 ohms, we get 8 volts. Note that 8 plus 4 equals 12, the battery voltage as it should. The voltage across the capacitor equals the voltage across the 8 ohm resistor, since they are connected together at the top and the bottom. So the capacitor voltage is 8 volts. And the charge in the capacitor, QC equals CVC. So we have 6 microfarads times 8 volts, giving 48 microcoulombs. Now let's look at example 2. This is the same as example 1, except now we have a 24 ohm resistor in series with the capacitor. And we want to find the circuit parameters immediately after the switch is closed and a long time after the switch is closed. Let's look at case A, immediately after the switch is closed. We close the switch. Current I flows through the battery. At this junction, it breaks up into two parts: current I1 through the 8 ohm resistor and current I2 through the 24 ohm resistor. Note that I have removed the capacitor because immediately after the switch is closed, the capacitor acts like a short circuit. Now I can find the equivalent of these two resistors, the 8 ohm and the 24 ohm. They are in parallel, so 1 over R equivalent is 1 over 8 plus 1 over 24, which is 1 over 6. So R equivalent equals 6 ohms. So now my circuit becomes this: a 4 ohm resistor in series with a 6 ohm resistor. Let's find the equivalent resistance. 4 plus 6 equals 10 ohms. So this is our circuit: 12-volt battery across a 10 ohm resistor. Let's find the current I by applying Ohm's law. I equals V over R. 12 volts over 10 ohms, and we get 1.2 amps. Now let's find the other circuit parameters. The voltage across the 4 ohm resistor. Apply Ohm's law. 1.2 amp current times 4 ohms gives us 4.8 volts. The voltage across the 8 ohm resistor equals the voltage across the 24 ohm resistor because they are in parallel. We take the battery voltage, 12 volts, minus the voltage across the 4 ohm resistor, 4.8 volts, and we get 7.2 volts. Note that 7.2 volts plus 4.8 volts equals 12 volts, as it should. The current I1 through the 8 ohm resistor, applying Ohm's law, V over R, 7.2 volts over 8 ohms gives us 0.9 amps. The current I2 through the 24 ohm resistor, applying Ohm's law, 7.2 volts over 24 ohms equals 0.3 amps. Note that the sum of I1 plus I2, 0.9 plus 0.3, equals a current 1.2 amps going into this junction, as we expect. Now let's put the capacitor back. The voltage across the capacitor is 0 volts, and the current, QC equals CVC, is also 0. It is 0 coulombs. Now let's look at the case a long time after the switch is closed. We close the switch, current I flows through the battery. At this junction, it divides into current I1 through the 8 ohm resistor and current I2 through the 24 ohm resistor and capacitor. After a long time, the current through the capacitor is 0, so I2 equals 0. From Kirchhoff's junction rule, I equals I1 plus I2. Since I2 is 0, we find that I1 equals I. So all the current goes through this loop. And we can just remove that capacitor from the circuit. It acts like an open circuit after a long time. So our circuit becomes this: a 4 ohm and 8 ohm resistor in series as before. Total resistance is 4 plus 8 equals 12 ohms. Here's our circuit: 12 volt battery voltage across a 12 ohm resistor. Applying Ohm's law to find the current. I equals V over R. 12 volts over 12 ohms is 1 amp. Now let's find the other circuit parameters. I is 1 amp, I1 is also 1 amp, and I2 is 0. V over the 4 ohm resistor. Apply Ohm's law. 1 amp current times 4 ohm resistance is 4 volts. V over the 8 ohm resistor. 1 amp current times 8 ohm resistor gives us 8 volts. As expected, 4 plus 8 equals 12 volts. The voltage across the 24 ohm resistor is 0 volts because no current flows across the 24 ohm resistor. the voltage across the capacitor must equal the voltage across the 8 ohm resistor, since there's no voltage drop across the 24 ohm resistor. So the voltage across the capacitor is 8 volts. And now the charge in the capacitor. QC equals C times VC, so 6 microfarads times 8 volts gives us 48 microcoulombs. Here is our final example. The switch in the circuit of example 2 has been closed for a long time. It is then opened, and we want to find the circuit parameters immediately after the switch is opened and a long time after the switch is opened. Examples 1 and 2 were for charging the capacitor. Example 3 is for discharging the capacitor. Let's first look at the case immediately after the switch is closed. Immediately after the switch is opened. So, a long time after the switch was closed, as we saw in example 3, VC was 8 volts and QC was 48 microcoulombs. And the top terminal of the capacitor was positive because it was connected to the positive terminal of the battery, and the bottom terminal was negative because it was connected to the negative terminal of the battery. When we open the switch, current starts to flow. No current flows through the 4 ohm resistor and the 12 volt battery because the circuit has been opened here. So we can, just to make things simpler, let's just remove that part out of the circuit. So this is what we have. To a 24 ohm resistor in series with an 8 ohm resistor. We can find the current I by applying Kirchhoff's loop rule. Let's start here at the negative terminal of the capacitor and go around like this, back to the starting point. So we have VC, the voltage increase when you go through the capacitor, minus the voltage decrease across this resistor, 24 ohms times the current I, then minus the decrease across the 8 ohm resistor, 8 ohm resistance times the current I, and the sum of these must equal 0. Let's put in the voltage of the capacitor, 8 volts. So we have 8 minus 24 plus 8, 32. So 8 minus 32I equals 0, and I is 0.25 amps. So the voltage across the 24 ohm resistor is I times R, 0.25 amps, times 24 ohms equals 6 volts. The voltage across the 8 ohm resistor, IR, 0.25 amps times 8 ohms equals 2 volts. Note that 6 volts plus 2 volts equals the voltage across the capacitor, 8 volts, as expected. Now let's look at case B, a long time after the switch is opened. So a long time after the switch is opened, the current is eventually going to go to 0 because all the charge is going to be dissipated, and the energy of the capacitor will be dissipated into thermal energy in the resistors. So after a long time, the charge Q is going to be 0, the current is 0, and with zero current, 0 charge on the capacitor, the voltage of the capacitor is going to be 0 volts. And with no current in the circuit, the voltage across the 24 ohm resistor is 0 volts, and the voltage across the 8 ohm resistor is 0 volts. Here's a summary of what we've studied today. Let's look at charging the capacitor. Initially, the current is maximum. The charge on the capacitor is 0. The voltage across the capacitor is 0. The capacitor offers no resistance to current. The capacitor acts like a short circuit. In steady state, after a long time, the current through the capacitor is 0. The charge on the capacitor is maximum. and the voltage across the capacitor is maximum. The capacitor acts like an open circuit. Now let's look at the case for discharging the capacitor. Initially, the current is maximum, the charge of the capacitor is maximum, and the voltage across the capacitor is maximum. Capacitor acts like a voltage source. In steady state, after a long time, the current through the capacitor is zero, the charge on the capacitor is zero, and the voltage across the capacitor is zero. Thank you very much for listening to this presentation of the initial and steady state behavior of a capacitor. Giselle and I appreciate your attention. Please be sure to like and subscribe, and leave a comment in the space below. See you next time. Bye.